So can you guys see my screen? Okay. So I believe this was the sample problem that Professor Vivek gave us to use for the exam. Oh yeah, let me start the recording. So the recording started, right? Oh yeah, okay. Okay. Sounds good. All right. All right. So this was a sample problem that your professor gave us. So it says the first things first, there's a direct mapping with a write-through allocate on rightness. It says to consider a system of three processors, P1, P2, and P3, with the initial cache state shown. Assume if not provided, each data memory location has an initial value of 2, and the register is initialized to the initial value of 1. Determine the states of the change blocks in the cache of all the processors after each sequential operation. Okay, so first things first, what is the policy that we're using? It says we're using a write through on write miss. So it's a write miss. We allocate. So that's the process that they gave us. What that means is it's a write through policy, which means if I'm correct, there's a write back and there's a write through policy. So on the write through policy, if there's a miss, we're gonna allocate the value that's being loaded in currently. That's what it means. Because you can have a write through, write miss, allocate, and you can have a write through, write miss, do not allocate. You can also have a write back, write miss, allocate, and you can have a write back, write miss, do not allocate. So these are the four possible things that he can ask in the exam. Given that the sample that he gave us is a write through on write miss allocate, there might be a write back in your exam, but I'm not sure because for my exam, that's what he did. He said that he gave us the write through policy, so the on our exam the write back came. So yeah, all right. Now moving on from that, what does messy mean? So messy is MESI. The M stands for modify, so this means modify. E means um in a way it means that it's the only value, or I can't remember what the term he used, but it just means exclusive. That's what it means. Yes, exclusive. S means that it's in a shared state, and I means that it's invalid. Okay. So far we know what messy stands for. We know what's our policy that we're using. And now we see that it's a direct mapping. So what direct mapping means is that depending on the size of the cache, which in this case they told us that the size of the cache is, where was it? Okay, yeah. So the size of the cache is 2. 1, 0, 1, so the size is 2. What direct mapping means is that every single location that they give us, for example, is 3. When it's being loaded into one of these processors, what we're going to do is we're going to find the mod value of that value. So in the case of the first problem, it's asking us for 3 to be loaded in. So what we're going to do is 3 mod by 2, and that's going to give us 1. The second thing to note with these problems is that it tells you which processor you're working on. It tells us P1. So we know that there's 3 different processors right now. There's P1, P2, and P3. But it told us that it's acting specifically on processor 1. And then with the direct mapping that we know of, it's going to be 3 mod by 2, which is equal to 1. Do we follow so far? Are there any questions? Let me just check the chat, see if there's anything. Okay. So far we're all good. Great. Okay. Now, what you're going to know for the exam, he says, do not write back every single line. Just write back the lines that are being updated. Because if you write back the lines they're not being updated, sometimes it confuses you, and then you make changes to the question that aren't supposed to be. So in the first question, it's 3. So what we're going to do is 3 mod 2, which is 1. And in processor 1, that means we're replacing the address with a 3 inside. So what happens is we're going to look into our processor. And currently in processor 1, 3 is there, but it's an invalid state. So that basically means that 3 isn't there because it's invalid. Now, on that because of our policy of write through, to us, that's a write miss. So because it's a miss, we're going to allocate. So what happens is there's a bus, and the bus connects processor 1 to processor 2 and processor 3. All of these processors are on this line. While you're trying to allocate, going to main memory, what's going to happen is processor 2 and processor 3 are going to snoop. I believe you used that term in your class. So they're snooping, meaning that they're looking at what's happening on the bus currently. So processor 2 is going to look at it. Processor 2 in their cache 1, they don't have 3. So to them, it's of no value. Processor 3, however, is going to snoop, and in their cache 1, there's a 3. And it so happens that it's in the exclusive state. So what processor 3 is going to say hey, processor 1, I have 3 in my cache loaded right now. So what I can do is I can share it. So because it's going to share it, that stops us from going all the way to memory to get the data, but we can get it from a next cache that has the data loaded inside. So currently in processor 1, the 4 and the E is going to remain the same. You don't need to fill those in, but I'm just filling it in for the purpose of teaching the concept. We know that 3 wasn't invalid, but in cache 3, it was exclusive. So because it's exclusive, it means that only cache 3 had the data right now. But to be able to share it, what we're going to do is we're going to change the exclusive to a shared. So this is the process of how messy works. From a modify, you can move to an exclusive. From the exclusive, you can move to shared. And then from shared, it goes to invalid. So currently, we're in the exclusive state. We want to share this data across the processor 1. So what's going to happen is that 3 is going to remain in P3, but it's going to be in a shared state. So the E is changed to an S. And then processor 3 gets the data from processor 1, sorry, gets the data from processor 3, and then it changes to a shared state. Does that make sense so far? Let me check the chat. Do you have any questions of what happened so far? What transpired?
Wait, can you explain how it changed to shared state inside processor 1? I understand why you said processor 3, but why it's shared state in processor
Okay,
1?
good. Yeah, no problem. So remember, processor 3 was exclusive and it changed to a shared state. When it changed to shared state, it's sharing that data across the processor 1. So what the shared state means, or what it's telling us, is that there are 2 processors at least that currently have the same address inside. So that shared state that processor 1 is holding, it's telling us that it's sharing that data from processor 3 and processor 3 and processor 1. They both have that 3 inside. So they're sharing that. It's not exclusive. When it's exclusive, it means only that processor or only that processor's cache has that specific memory address. But in this case, it doesn't have, it isn't the only one that has it. Does that make sense?
Okay, so it's like a mutual thing. Once it's shared with processor one, it's like overall within the memory, it'll
Yes.
into a shared state. Okay, okay.
Yes. We're gonna see a bit of a difference because this is just a load word. We're just loading into the system. So for this one, it's just gonna be shared. However, with a store state, that's gonna be a bit different if you had to share data across. So we'll see that in the following questions. But for now, this is just for the load. This is how it works. If there's any questions, you guys can let me know. I can go over it again. Or if not, we can move on to the second part. Are we all good with this one? Okay, great. All right. So currently, okay, so what I'll do, I'll just rewrite the states inside the boxes so that it's easier when we scroll down for the rest of them. Forward and I. Okay. So currently this is what our three processes look like, and this is what the cache allocations look like inside of the three inside this line. Okay. So moving on to the next one. In the second line, it says that we're acting on P2. So we're not bothered about P1 and P2 and P3, sorry, currently. We're just looking at what's in P2. In P2, we're doing a store operation. Now, with the store operation, okay, I'll go through the store operation in a few. So we're gonna do because it's direct mapping, we're gonna do the mod of 8. In this case, when we do the mod of 8, 8 modded by 2 is gonna be 0 because 8 divided by 2 is equal to 4 and the remainder is 0, which is the mod. So we're looking at processor 2, but we're looking at the cache of 0. Currently, in the cache of 0, what we have here is the 8 is currently inside. So the 8 is currently inside, and it's an exclusive bit. Since P2 already has the block 8 in an exclusive state with the write through, the memory is updated and immediately the cache stays the same. So it would effectively just be 8. Does everyone follow with this one? Nothing really changed because we're doing a store word on the second line, and currently in the cache of that specific allocation that you're looking at, which is the 0, 8 is already there in its exclusive state. Are we all good with this one? Okay. So I just fill in the rest. 1 E S. Okay. So that's currently how the cache is looking for the third one. Move on to the next line, the P3. So for P3, they're telling us that we're loading the memory of 3 into P3. And after doing direct mapping, we know that 3 mod by 2, because the size of the cache is 2, it's going to give us 1. So we're looking for this line specifically. This is the line that I'm looking for. Currently, in this line, I have P3. So P3 is already here. And yeah, P3 is already here in the shared state. So this would be a hit because unless it's a write, unless we go through the cache and we miss, that's when we activate our policy. But in this case, 3 is already here. There's really nothing to do. So there's no change in this line. There's no state change. So you can, I think if there's no change, he says that you can leave it blank and you get the points, if I'm not mistaken. But I'll just write it in for the sake of the explanation.
I have a question. So you're just looking at the P3 from before? or the
Yeah,
whole.
you're looking at P3 from before. So this is what P3 has inside currently. The
Okay.
three in the shared state.
Wait, and since you don't have to go back to main memory, since the three is already there, there's you just rewrite it there. There's no
Yeah,
issue.
because remember, the policy only activates when we have a right miss. So for
Okay,
us, there's well, as long as we get a hit, we're good. That's what we're looking for.
got
But
it.
the policy only activates when there's a miss. Because when there's a miss, we're gonna go on the bus, and then the processors are gonna snoop. And when they snoop, they're gonna let us know if they have the data for that cache. If they do, then we're gonna share the data, or we're gonna change the state, and then we're gonna allocate it to the previous processor. If they don't, then we're gonna have to go to memory, and then we take that memory, we take that specific memory location, we fill it, and then when we fill it, that's gonna be an exclusive because no other processor has that data inside. But if it's a hit, we have nothing to worry about. We got what we wanted from it. We can move on to the next stage. Does that clear up the question?
Yeah, got it.
Okay, no problem. So now for the first one, it's saying we're doing a store word. 4 is the memory location, and we're doing this in P1. So P1, we're gonna take the 4. Again, it's direct mapping. So 4 modded by 2, it's gonna go to 0. So we're looking for 0. That's the cache we're looking at. Currently, in P1, the block already has 4 in its exclusive state. So this is a write hit on the write through policy. You don't need to do anything else because 4 is already here. So this is fine. Okay, good. So we're fine with this one. Any questions on this one?
No.
Okay. Now the fifth one, it's saying that we're acting on P3, so we're in processor 3, and then we're loading 4. So when we do 4 mod by 2 again, it's going to be processor 3, cache of 0. Now currently in my cache of 0 in P3, I have 4 and it's in an invalid state. So lucky for me that it's in an invalid state, that means that basically nothing is inside. So then there's going to be a miss. And now I'll look from the 3 processors. So on my right, because remember my policy is a write through on write miss allocate. So on allocation, I'll send, hey, I need 4 inside of P3. Then P1 and P2, they're going to snoop. So P1 and P2, they're going to snoop. I see in P2, there's an 8 in the exclusive, so P2 can't help me. I look at P1, P1 has a 4 in the exclusive state. So therefore, similar to the previous line where we had the 3 in the exclusive, the same process is going to happen again for the load word. So we have the 4 on the exclusive, but because P3 also needs the 4, 4 is going to be shared to P3, and it's going to be in a shared state. So we're going to scratch the E, it's going to write as S. The other states and the other addresses, they're unchanged because for this specific line, nothing else was going on. 3S. Okay. Are we good with this one? Okay. All right. This is line 1, 2, 3, 4, 5, 6. Okay. We're on line 6. So for line 6, what we're doing here is, so I think there was a mistake here. There's supposed to be some some process that's in front. So I think he made an error here on this line. Usually there's an error like this, we just give you the free points for it. But I think there's supposed to be something here because it tells us like what the allocation is. I believe when we did it, he did say it was a store word, so I'll work with it as a store word. So I'll just put store word here. Now we're looking at P1 again, and we're doing direct mapping. So it's 4 mod by 2. Let's give it 0. So P1 cache 1. Currently, in P1 of the cache 0, 4 is already there and it's in a shared state. So given that it's in a shared state, what's going to happen is that, well, this is a store word. So because it's a store word, if you recall how stores work, it would be fetch, decode, exec, and then the mem stage, right? So what's going to happen is that because of the fact that it's a store word, it's going to store the data that's going to be in the address. But at the same time, it's going to update the main memory. So it changes the state of the 4 to be, it's going to be invalid, then it's going to change to modify, and then it's going to change to exclusive. Now, that sounded like a lot. So what I'll do is, yeah, okay. So what's going to happen is we have the 4 here, and currently there's a 4 here in a shared state, and there's a 4 here with a shared state inside of my P3. Now, when we do the store word, we're storing something inside of this memory address. In the load word, we're going to these addresses, we're taking whatever's inside and we're loading it into the cache. But in this case, we're storing something into that memory location. So that means if the memory location had like a value of 5 inside, well, now I'm storing something else inside, which is like a 6. Now, because I'm storing something new inside, even though the memory address is inside the cache, that doesn't stop the fact that we're storing something new inside of that memory address. Does that make sense?
Wait, can you repeat that?
Sure. So remember with the store word, right? And the load word? With the load word, I'm loading from a memory address. I'm loading some value, like let's say in this case, I'm loading from this memory address 4, whatever this value is, I'm loading it into T2. But in the store word, I'm storing whatever is in T2 into this memory address. So on the load word, when the memory address is already in the cache, I don't need to do anything because all I'm doing is loading whatever is in that memory location of 4 into some variable, right? But in the store word, the T2 could be some other value and is trying to store something new into the memory address. So even if the memory address is inside of my cache, that doesn't mean that the memory address is up to date with whatever value it is currently being added into that memory location. Does that make sense?
Oh yeah, that makes sense.
Okay. So because of that fact, that's what I was saying with the store words, they're a bit different. The load words, they're a lot simpler. You're just loading. But for the store word, even if it's in the cache, there's always something you need to do. So because the store word, we're storing T2's value into this memory location, what is going to happen is, according to my messy diagram, the process that follows after the shared state would be invalid. And that makes sense because of the fact that when I update the value of the memory address in P1, which is the 4 in P1 currently, this is now going to be changed to invalid, then it's going to be changed to a modify because the data inside of the memory address would have been modified. And then because it was modified from the main memory on my write miss policy, it says allocate. So then I would have to change this to exclusive. Now, when I make the change to the memory address, that also means that every other cache that has the memory address of 4 is also going to become invalid because remember, this update is only happening to P1. It's not updating every single processor, only the processor in P1 with the cache. So what's going to happen is that in my P3, the memory address of 4 is there, but the state is going to be changed to invalid. Does that make sense?
Yeah, it does.
Okay. So once the state of the address changes from shared to invalid, the P3's memory address of 4 is going to be invalid. But because the update is happening inside of P1, when it changes to modify, it's going to be changed to exclusive because of my write miss policy, and it's going to allocate. So that way it changes it back to exclusive because it's the only memory address of 4 that has the modified data inside of it. So it's going to be changed to exclusive. If anyone has any questions about this one specifically, you can send the question in the chat, or you can ask your question.
Can you go over again the state on P1? How'd you get exclusive?
Sure. So when I had memory address 4, so it's okay. So for 4, P1 has the block 4 inside, and it's in a shared state. So let me just erase this, this, and this. So currently in P1 of cache 1, because it's 4, I have 4 inside as the memory address. Now, 4 is in the shared state. Just as in P3, it's also in the shared state. Both of the caches, they share this block 4. But what's happening on P1 is that a store process is happening uh, in that block of 4. So a processor can't exactly write to the block if it stays shared. Therefore, it needs to be changed. The state needs to be changed of the block. Now, when we're adding a new data, because T2 has a data, and according to our process, it's a store word, we're storing whatever that data is into the memory address of 4 in the P1. So therefore, when the new data goes into that memory address, it's going to change the state from currently whatever value is inside of it, it's going to be invalid. But when we change the value inside of the memory address of 4, it would change the invalid to modified. Likewise, on the P3 side, because the value would have changed in memory address of 4, memory address of 4 is now invalid because it doesn't have the most up-to-date value that's inside of the memory address 4. Now, because the memory address 4 had been modified, and it's the only cache currently that has the address 4, after the write through, write miss, allocate process, because it was a miss, what's going to happen is that the modify is going to be updated to an exclusive. Now, the reason why it's also an exclusive is because when you have an exclusive, let's look at the original here. We see that P4 was exclusive, and the reason why it was exclusive is because even though P3 had the memory address, P3 had the memory address of 4, but it was invalid. Because it was invalid, P1 was the only processor with a cache that had 4. Therefore, it was an exclusive state because it's exclusive only to P1 and the cache is 0. So it's the same idea is going on here. When we made the update, even though they were shared, the update happened, so the value inside of P4 is no longer the valid value. Therefore, they were both invalid. And then the modified value was stored inside of the memory address in the processor 1 of cache 0, and that memory address was 4. So it was modified. But then, after we did the modification, our process tells us that it's on write through. When there's a write miss, you need to allocate. So because the allocation is happening, that value that was updated inside of the main memory somewhere over here, when that value is changed, it's going to be shared all the way back into cache. So therefore, it becomes exclusive. Does that help with the question? Or
Yeah, I understand it now.
okay. Is there anyone else that also has an issue with this question? Or we can go on to the next one. Okay. So moving on to the next one now. Let me just update the caches so it's shared. This should be 3 and S. Okay. So for the P2, a store word's happening again. And it's going to be on P2, the memory address of 4. After direct mapping, we know that's going to be P2 and the cache 0. So we have 4. Okay. Yeah. So when it goes into the cache, currently P2 holds 8 and the exclusive state. Mm, P2 is in the exclusive state. So therefore, it's in the exclusive state. 4 is currently invalid. There's a memory address of 4 with the exclusive value there. And we're storing the new value into P4 with the memory address. So 8 is going to be changed to 4. That state's going to change as well. Oh yeah, so there's a miss on this policy because we went through the write. So it's a write through, write miss on the miss we're gonna allocate. So we missed because the fact that 4 is not inside the cache. And because 4 isn't inside the cache, then we currently put the value on the bus. So P1 has 4 in the exclusive state, and P3 has 4 in the invalid state. Okay. So this invalid state is going to remain. We're not doing anything with the P4 because technically when it's invalid, it basically means that there's nothing inside of P3 in that slot currently. However, the only cache we need to be, what we need to pay attention to would be the one inside of P1 that has a 4 in the exclusive state. So on the write miss policy, we're going to go on the bus and we're going to say, hey, we need 4 because 4 is the memory address that we need to store something into. Then P1's going to snoop. It's going to say, oh, we have 4 currently. So then you're going to say, okay, we can borrow 4 from you. So therefore, the exclusive state of the 4 is going to be changed to a shared state. So now we have 4 inside the cache, and it's going to be in a shared state because we're sharing it from P1. P3, sorry, is still invalid because nothing's happening on that one. That's just invalid over there. But now, after we would have done our policy, we still need to do the process of the instruction, which is the store word part. So now after we would have gotten shared state, we're now going to do the store. By storing a new value into the address, is going to make the address. So it's MESI 4 is going to go to the invalid state because it will no longer have the value, the current or most updated value. So it's going to go invalid, then into the modified state. The value would have been modified from whatever's new value that's given to it from the T1. And that means that because we had a state change in P2, the shared state that's inside of P1 is going to be lost and it's going to be invalid as well. Now, the modified value, let's say P4 had 5 from the previous line. Well, P4 now has 6 because 6 was given to P4 from the statement of the store word. So the modified state is inside of P2 with the memory address of 4. After it would have been modified, there still needs to be the main memory. And what it's going to do it's gonna update the main memory on our write-through policy. So because of that update, the modified state is gonna be changed to an exclusive state because for the memory address of 4 in P2, that's the only processor with a cache that has the memory address of 4 with its most up-to-date value. So therefore, it's exclusive. And the rest of the cache remains the same. So it would be E, 3, and S. So the final closing of this line would be the fact that the memory address of 4 went to invalid because it no longer has the modified or the new value that's stored inside of the memory address of 4 currently, but P2 has it. P3 was invalid from the previous line, so given that P2, sorry, has the memory address of 4 with its most up-to-date value, then it's going to be the exclusive one. Does that make sense? If you have any questions, you can let me know about this particular line or any of the lines above throughout the entire process if you were lost with any of them. And was this also in the document? Hold on. I'll check the document to see. Just give me 1 second. Okay, yeah, so there's a second part to this. If you guys have no questions with this one, we'll move on to the second one. It's a different policy, so it's gonna be completely different. But yeah, if there's no questions, we can move on. Or if not, if you guys have another topic you want to go through, because the messy kind of took a little bit of time. We only have an hour left, so if there's another topic you guys want to go through, we can go through that. If not, we can work the second messy problem. It's up to you guys.
Are we able to just go over the specifics of the right through and right back policy, or and as I said, like the four on the top of the last paper that you had?
So you'd like to go through the policies, the four policies, correct?
Yeah, these the difference between them.
Okay, sure. So, if I can get a clear page. Okay, so there is a write through and there's a write back. By show of hands, or does anyone have an idea? Anyone has an idea as to what these policies are from class? Does anyone wants to try to give an idea as to what it is? There's no right or wrong. We'll correct it, but you can just make an attempt. Or you can let me know like what you do know from it, and then we could like build from that.
For write through, I'm guessing you just like if we have like a head, like, I'm guessing you just like update the cache and update like the main memory.
That's good. And then on the right back,
We basically just update the cache, but we don't update the memory unless we actually need to.
yes. So that's exactly what the write through and the write back policies are. The write through, what it says in the write through is that I'll make changes in the cache. So this is my cache. So I'll make changes in the cache, but also when I make those changes, I'm making the changes in the main memory as well. On the write back policy, I'm only making those changes on the cache. Does that make sense?
Yeah.
Okay. Now, since we have the policy, the start of the policies, we're going to move on to the second part. So your policies are always going to be either write through or write back. And it's going to be followed with a write miss on both of them. Okay. Now, what this means is we're doing the policies, but these policies only are enacted or they're only useful to us when we have a write through with a write miss. What that means is the policy only works when we miss in the cache. So if the data is already in the cache and I'm loading that data in the cache, I don't need to worry about my policy. But if it is that I'm trying to load from the cache, because remember, what is our cache? Our cache is this little box here, right? The main memory is the bigger one. What I'm doing in the cache is I'm taking data from the main memory over here, and I'm storing them one by one into the cache. The cache is never as large as the main memory. So it's going to store bits and pieces inside of my cache. So let's say this is 1, 2, 3, and 4. It's going to store 1, 2, and 3 inside of it. If I want 1, 2, or 3, what the cache does, it speeds up my process of having to go to the main memory. Because we know in our fetch stage and our mem stage, it takes us around 30 nanoseconds to be able to move from the processor's over here, the main memory's here. It's 30 seconds to move to the memory, get the data we want. So therefore, if we can have the cache where it loads the data from the main memory inside, yes, it's going to be 30 seconds for the transfer to be to the cache. But if I ever want 1, 2, or 3 for any process, it's going to be like 2 nanoseconds. So I'm saving myself time by storing instructions, like frequent instructions, into my cache. So the idea is I'm storing the frequent instructions in cache, and whenever I call upon those instructions, if I want 1, 2, or 3, I can just pull them from the cache. And it's going to save me time. Rather than going to main memory every single time I want to use this data, it's going to be 39 seconds, 39 seconds, 39 seconds. And if you have like 100 lines of code that you're doing the same thing 100 times, then it's going to add up to a lot. So that's the idea of having the cache. So on write miss, we can either have an allocate or a do not allocate. On the write back, write miss, we can have an allocate and a do not allocate. Now, does anyone wants to try to explain what the allocate and the do not allocate means? Again, there's no right or wrong answers. You can try, and we'll figure out the rest.
So I think this is where my confusion comes from. So is the allocation, is the cache being updated? The cache being updated, or well, I don't have any other option. Like you basically grab it from the memory and update the cache.
So, what? Yeah, but in a way, kind of. So what happens is on a right miss, let's go with the right through, the right miss allocate. Sorry. But what it's gonna do is that on a right miss, what I'm doing is I'm gonna say, hey, I missed the data, I do have it. So I'm gonna bring that block into the cache. So on the allocate, it's telling me I'm going to main memory. If it is, in the case of, let's say, okay, yeah, let's go with that like the simpler part first. We'll explain the processors part after. So I'm dealing with one processor right now, and I have a size of 2. So this is my P1. This is my cache for P1, and it has a 0 and a 1. Now currently, I have some data that I want to put into the location of 0, but when I try to put well, I don't want to put it, sorry. I'm not putting the data inside. I'm trying to call the data from 0 in the cache to be able to use that in my process, in my instruction. But when I look at the cache inside of 0 currently, it has like a value of 5. Let's say 5's in there. But I want like 7 from that cache, but it's not there. So what it's gonna tell me is that I went through the cache and I had a miss. Now on that miss, I need to get that data. So what I'm gonna do is I'm gonna go to the main memory. So now I'm gonna travel all the way to main memory over here. Now, depending on what my policy says, in this case, it's an allocate. What I'm going to do is I'm going to bring that block of data into the cache. While bringing it to the cache, I'm writing it to the cache. And I'm also writing to memory at the same time. That's what the allocate does. It's bringing the data into the cache, and then whatever changes are made to that specific memory address that I brought from main memory, I'm updating it inside of the main memory as well. Whereas if there was a write through, write miss to not allocate, what it would have done is that I have the cache here, 0 and 1, 7, 6. I wanted to bring 7, but 7 is not here. So I went to the memory, and what it's going to tell me is to not bring the block into the cache, just go straight to memory and make the update inside here. So if it was that I wanted the 7, well, the 7 isn't inside here. It isn't inside this block. So what's going to happen? The store word process or the load word process that's here, it's not going to happen inside of the cache. It's going to do whatever. It's going to go to main memory. It's going to look for 7. It's going to do whatever operation it is inside of 7, and it's going to update the main memory. So now 7 probably holds maybe some value of 20 instead of 10. Or I loaded the value from 7 into that specific instruction. I stored it into like some register T1, but nothing ever changed in the cache. So the cache still has 5 inside. There are benefits to having the do not allocate and the allocate. With the allocate, you're always updating the main memory and the cache at the same time. But for some cases, it might be better. I mean, it's always better to have the allocate, but there's some niche cases where the do not allocate works because when you don't allocate, that 5 still remains in the cache. So if I ever go, like let's say the following instruction is using 5, well, I never brought 5 into the cache. So 5 is I never brought 7 into the cache. So 5 is still there. So I can use the 5 for the next instruction. It saves me time. But if it's not a case like that, where it's like the following line is probably going to ask for 7 again, I'm going straight to memory and I'm making the update there. Does that clear up the allocation and do not allocation part?
Wait, so if you have a messy problem, like the one we did previously, and you have a do not allocate, you would the value inside the cache wouldn't change, right? Because you're only updating it in the main memory.
In the main memory, yeah.
So you just write the previous value.
Yes.
Okay. Oh wait, would
Do
there would the states be manipulated? Would be a change in a messy problem if it's a do not allocate? Like
Yeah, it would change. It would change.
It's just the states, and then you would just okay. I see. I see.
I think the next one is so it's a right back allocate. That's what it is. So given that he gave us a right back allocate and and a right through allocate, it might be possible that in your exam you get one of these, or you could get the do not allocate for the exam. Um, but yeah, this is the material he sent us. So I guess we can go through this one because I'm not sure if you're gonna get something similar to this.
I'm sorry. So on the do not allocate, are we just essentially making it invalid, the state's invalid?
On the do not allocate,
Yeah, so if it's updated, if it's a write through policy and it states just to update the main memory, and you say that we're not updating the cache, uh, are we essentially just making the states invalid, to show that hey, this may have been updated in main memory, or do we just leave them as is?
um, okay, so if I'm getting your question right, you're saying if there was a process and we went to the processor, P1, and there's a cache, and you try to get the data from there, but it's not there, so it was a miss. We're gonna have to go to main memory to get the data from the main memory, correct? And then you're asking if in the cache, would that mean that the cache would be invalid for the following state?
Well, specifically if it's a do not allocate, and we do go to the main memory, you said that uh, the state is updated, right? So what exactly is the state updated to? Is it updated to invalid and we just don't change the address or um yeah.
Well, I can't give you a definitive answer because it depends on what the state is currently inside of the cache. So it would depend on what the state is in the cache at the point in time. Then it's gonna change from that. So I wouldn't be able to tell you like it's gonna definitely change to invalid or not, if that answers your question.
So let's say we have an exclusive state in the actually not even exclusive. Let's say that it doesn't exist. Let's say the address doesn't exist, right? So can you go back to the other one and go all the way down? So let's say we have a shared, or not even a shared. So where was the one that we updated the four entirely? This one right here, P2 in the last block. So we replaced eight with four, right?
Yeah.
Um, if it's a write through on a write miss and do not allocate, then how do we handle that for P2? Do we just update the main memory and not update this address, um, but just update the state to say that it's invalid?
So
Or
on
maybe
the
I'm just
right,
overthinking.
okay, so on the right through there was a right miss. And we'll change this to a to now. Okay. Okay. So on the right miss, we're gonna do not allocate. Therefore, the current state would have been, so I'll just do this and this. Okay. So this is exclusive currently. This is A, this is E, 4, and I. Okay. So on the miss, do not allocate, which means on the do not allocate policy, what we're doing is check this. So on the right miss, if the right miss occurs dependent on the will be updated only. I see. Okay. Will not be brought into the cache. So for the main memory is over here. 4 is inside this main memory currently. There's some other blocks of data inside. And in the main memory, 4 is inside. So the update is going to happen inside of the main memory. So we're going to store, let's say 4 currently holds 20 inside, and T1 has like 10. On the rightness, I'm not going to worry about the cache because the cache has 8E inside. What I'm going to do is I'm going to go to the main memory and I'm going to update the main memory. So now 4 is equal to 10. So then that means that this state is now going to be invalid because this doesn't have the updated value inside. This is already invalid. The 8 remains itself. It's the same. That's what's going to happen.
Okay, sounds good. Thank you.
Does that make sense of what happened?
Yeah, that makes sense. Hypothetically speaking, well, I mean, I guess it's safe to assume that he's not going to use a do not allocate. Um, it's most likely going to be allocate so he can see the work, right?
I'm not too sure because I remember did you guys have a review session already with him?
Yeah.
Yeah.
Did he give hints as to what's gonna be on the messy or anything at all?
I he did do a practice exam with us. I was actually gonna say I could send the file to the practice exam. It's in the chat right now.
Oh, okay.
Yeah.
Sounds good.
The last two questions. One of the last question is a write back to not allocate.
Okay, you sent it in the chat.
Yeah.
Can you resend it? Because I can't find it.
Oh, I sent it directly to my bad. I'm gonna send it to all. Um. Yeah. Just I just sent it.
Okay, got it. All right. Let me-
Oh, I sent the one with the answers in it. Would you want me to send the blank one
You
instead?
can, yeah, you can send the blank one as well.
Okay,
Because
I'll
I'll
send the blank.
just check back with his answers to make sure
Yeah,
that
yeah, yeah.
we're
I'll
doing
do that
it
right now.
correctly. All right, so I'll save
Um,
this one on my PC.
share.
Yeah, so you were saying in the one in class, he did, you see for this sample.
Well, he went through all these ones inside class. So, but this was the review that we did.
Okay, so he did a direct mapping, the write through, allocate, on write miss,
Yeah, I sent
allocate.
them
Yeah,
the.
so
I
given
sent
that
them.
the sheet that he gave us to do for the review was a write through, allocate, and a write back allocate, I think it was as well, if I'm not mistaken, because this is the sheet he gave. So he did a write back allocate. So I think it's possible that he'll do maybe a do not allocate for your exam. It could be. Or it might just be one of these two. Because I'm looking at it and there's a right back. Um, but the right back allocates are the harder ones. The one with the allocation, those are harder than the do not allocate. The do not allocate is that you're just updating the main memory or whatever's in the cache that currently holds that memory, it goes to invalid. That's pretty much how the state works overall. If it's an exclusive, it would change to an invalid. If it's in the processor, then he'll just use it because it's going to be a hit. So I think I think personally the allocates are a lot tougher to do than the do not allocates, which is probably why he doesn't stress that much on it.
I sent the blank one inside the chat.
Sounds good. Should be- Did I? Okay, this is this would be okay. Okay, so we can work this one. I'll work it back with you guys. We'll go through it. So it says here that you have a write back. Uh, Can I? So you have a right back, a right miss on allocate. Let me just check the chat to see if there's any other questions. Where did the 1-bit thing come in? 1-bit. 1-bit. I'm not sure what the 1-bit thing is. Do you know what question it was from specifically? The change bit? Oh, yeah. I know there's a change bit, but I think that's for disk after disk scheduling. What was the last topic you guys did? Messy?
Yeah, the last one was messy, I believe.
So a 1-bit change? Um, it was right before messy. Okay. Do you have an idea what the topic before the messy was? Oh, it was the last. Oh, the last question. Okay. Oh, you're talking about the cache mapping? The 1-bit for cache mapping. If it's the cache mapping, there's a two-way set associative for the least recently used. Are you guys good with cache mapping? Because this is 3 points on the exam. This is the easiest part of the exam, and it's worth like 40 points on the exam out of the 100 points, I think. Keep scrolling, okay. This was the first question. The second one.
Isn't that
There.
just understanding fully associative versus and like there's LRU first in first out and then there's uh
Yep. So
yeah.
it would be like, okay, you have a cache of three, of four, sorry. One, two, three. And then you look at the list that you have, and depending on the type, if it's least recently used, then whatever is least recently used, that's the one that you're gonna replace inside of the mapping. So,
Okay, I got you. And then he'll give like two parts with two different uh mappings, I guess.
yeah. So it's gonna be like two questions for your exam,
Or three, yeah.
and you just gonna do the mappings. So it's a simpler part of the exam. I think like this part. I think this part on your own, you could be able to like figure it out because it's just not much. There's direct mapping, there's fully associative with the least recently used, and then there's two-way. So the two-way, I think that's the bit when she's talking about. So two-way means that if you have a cache of size 4, what it's gonna be is that because it's a two-way, it's gonna be 0, 1, and then I guess you use 2 and you can use no, use 0, 1 as well. I think that's it. So what it means is that depending on when you do the mod of the individual values, if I'm not mistaken, it tells you which one of these. So this is technically 1 and this is 2. So I think so. This could be 2 and 3, if I'm not mistaken. I'll just check what he did to make sure that it's the same thing. Yeah, so that's what he did. So he did 0. He did 0 and 1. That's what he did here. So you're basically dividing your cache into the the ways that he says. So if it's a two-way, it's gonna be the size of your cache, which is 4 divided by 2, so you know it's 2 in each one of these. If it was like a four-way, it'd be 4 divided by 4. So then it's gonna be one is its own, this one's its own, this is its own, and this is, and then from then you just do the mapping of the values. So you do 7 mod by 2. 7 mod by 2 is gonna give you uh 1. So therefore it's gonna fall in this cache. So then you put 7 inside of maybe the slot. And then the second one is 3. So we do 3 mod by 2. And it's going to give you the allocation inside of this one as well. So it's going to be 7 and 3. Then the next one is 1. So what I'll do, because it's the least recently used, my cache is filled right now. So because it's filled, I need to kick one out. But it says the least recently used that's the way I'm going to determine which one's kicked. So I have 7 and 3 is my data type. The data I put in, they're already filled in the cache. I did with the modulus of 1, and with the mod of 1, it tells me it goes into 1. So therefore, the least recently used one is a 7 because 3 was just added. So therefore, I'm going to kick 7 out, put 1 in, and then 3. Do you guys follow so far?
Yeah.
Okay, the next one is 2. So what I'll do is 2 mod by 2. That's a 0. So I'll put the 2 inside there. And then I'm going to rewrite whatever other numbers I have. Yep. Then there's a 5. I do the mod of 5. It's going to give me 1. So therefore it fills in this space. Then I look at the least recently used one. Well, 3 was added before 1. So therefore 3 was the least recently used one. So I kick 3 out. Then I go with 5 and then rewrite my 2. And then I just repeat the same process for the rest of it throughout. The hardest part of this is just making sure you remember the difference between the two-way and a four-way. Because in my exam last semester, he brought a four-way, and everyone thought that because it was a four-way, you're dividing it by, I think we all did divided by 4 or something. And it turned out that that's not what he meant. It meant that you were supposed to have 0 and 1, 0 and 1, 0 and 1, 0 and 1 for 4 different types. That's what it meant. And everyone lost marks on that one question. And because this mapping is worth 40 points in your exam, you mess up one of the mappings, you lose 20 points. So that kind of like messed with everyone. But yeah, I think he gave like a little bit of partial credit for it. But yeah, this question in particular, the one with two-way set, I highly recommend you review this one for your exam because there's a possibility that there will be one on the exam depending on which copy you get for your exam, because there's 2 copies for the exam. So whoever you're sitting next to, if they don't have the same copy that you have, it's going to be a different question for each person. The direct mapping is pretty straightforward, and the fully associated with the LRU, that's pretty straightforward. The only thing that gets tricky is the two-way set associated and the four-way. Once you get those, you're pretty much set for the cache mapping, and it's 40%. 40% of your overall grade. All right, we got like half an hour left, so I'll go through the messy. Um, I can try to go through the question one in like the last 15 minutes, but we can get through the messy, and I think like the messy is probably the one that you guys have more trouble with. This should be 3 points. Um, yeah, this is basically the same thing as the first question. Then what is this? This is a write through. Do not allocate on right. Okay, we could do this one actually. Do you guys want to do this one instead? Because this is a write through on right miss do not allocate.
Yeah. Yeah.
Are y'all good with this one? So I'll do this one. This was probably gonna take the entire half an hour because it's a pretty long one, but I think this one's gonna help a lot more. Sounds good? Okay. All right.
Wait,
Let's
I have a
see.
question before we start this one.
Sure.
So like let's say it was a four-way set associative. Would we divide that by the size of the cache?
Yes. So if the cache was 8, for example, because I think 8 was the one in my exam, it said it was a four-way. So what we did is that we divided the 8 into, I thought it was gonna be 0 and 1. So therefore it would be 1, 2. Okay, we do that. 0, 1, 2, 3. And then I did 4, 5, 6, 7 for the next one. This was wrong. What it was is that it meant that when you divide 8 by 4, there was 4 different well sets because it's a set notation. So it'd be 0, 1, 2, 3, and each one had their own set. Like that. That's what it was.
Okay, I got it. Thank you.
Yeah. That was pretty I think I still have a copy of my exam. somewhere. Just give me a second. So, okay, yeah. Yep, that's what you need to do. So it's four sets. So you need to divide it in this way, like this, not like this.
So whatever the set is basically how many blocks you're gonna use.
This set tells you how many sets you should have
Gotcha.
for, so let's say it was a four, the cache size of four, then four divided by four meant one. So there are four sets, but they each hold one.
Okay, I got you.
So it'd be 0, 1, 2, 3, but it would be 0, 1, 2, 3 inside here. Because even though it's a cache of size 4, you're doing four sets. It tells you how many sets you're making. Does that clear up the two-way and the four-way?
Yeah, it does.
Okay. Yeah, so just make sure you practice with those because that was a mistake that I think everyone in my class made for that exam. And he wasn't too pleased because everyone everyone made that mistake. It wasn't, yeah. All right. So we can do the right through right miss to not allocate. Okay. So we're gonna try to understand how the cache works. I think I worked this problem myself, if I'm not mistaken. Because this was a pretty long one. So I'll pull that up because it might be a lot helpful. Well, these are just cache maps. Okay, yeah. Yeah, so this is the same question, but I worked it on my own. So with this, it should be a lot simpler to do the explanation. So in the first line is a load word. And when you're doing a load word, you're loading whatever is in the memory address, you're loading that into the register. Is that clear?
Yeah.
Yeah. Okay. So that's just like a pointer because for the store words, what you're doing is you're storing from some register into the memory address. So you're doing the opposite, like this. I guess that's why he probably like bracket the register so it gives you an idea you're moving from here to here. And then from this you're doing from the memory address into the the register. So it says here in the question that the initial value is 2 of the general purpose register and the data memory location has an initial value of 4. The data memory location means this is the memory location, data memory location. This is your register. So these, anything that has a bracket like this with a number inside on the outside, this, this, these, not that, this one, all of them, they hold a value of 4. So this is 4. Therefore, when I'm loading the value, because what you're doing, you're not loading the memory address into the load word, you're loading whatever's inside of this memory address into this register. So currently, the 2 holds 4. So therefore, this 4 is going to be loaded into my my register T2. Everyone understands that?
Yep.
Okay. Again, if there's any other question, uh, the first one would be a two-way, right? What were you referring to about the two-way?
Oh, well, it was when you were talking about how you guys had a four-way problem and then you
Yeah.
wrote
Yeah, yeah,
your
yeah. Oh,
solution
okay.
originally?
Yeah, the first one would have been a two-way that I showed you from the exam sheet that you had, but the one that I had for my exam was a four-way.
Oh, okay, cool. Thank you.
No problem. Okay, yeah. If there's any question at any point, you can stop me. I'll try to explain as much as I can. So the second part, we're doing an add type. Just for reference, anything that's load, it has a fetch, decode, exec, mem, write back. Anything with a store, it's a fetch, decode, exec, mem. Anything with an R type, it's a fetch, decode, exec. You skip the mem stage, you do a write back. Anything for a branch, it's fetch, decode, exec. Anything for a jump, it'll be a fetch, decode, and undecode. It knows that it's a jump, so it's just gonna jump. This is important. You'll need to know this for the exam and for the rest of the semester. So there's just a pointer on the side. Now there's a one here. What we're doing, this one isn't a memory. It isn't a memory address. What it is, it's a value. If it was a memory address, it would have been governed by brackets. So when you see a one or a number like this, it just means it's a number. That's all it is. So the value currently in T2 is 4. So therefore, when I'm doing the add type, I'm adding whatever's inside of T2, which is currently 4, plus 1, which means it's going to be 5. And then I'm going to take the 5 and put it and store it inside of the register T1. Are we good with that?
Yep.
Okay. Now we're doing a store word. Now what you're doing with a store word is that inside of the T1 originally had 5 inside. But what I'm going to do is I'm going to store whatever is currently in T2 into the register of T1. So because the register of T2 holds a value of 4, then that means T1 is going to be storing 4. That's what's going to be inside. See? That's what your professor did as well. Storing the value of... Okay, I see. Okay. So, I see, I see. All right. So let me just clear this up. This is the memory address, right? Anything in the brackets, they're memory address. So when you see a bracket, this is a mem address. For load, what you're doing is you're taking whatever's in the bracket and you're storing it inside of a register, T of something. For store, what you're doing is you're taking whatever is in the register and you're storing it inside of the one that's in the bracket. So the register here is T1, and T1 currently has 5 from the addition. Therefore, I'm going to store T1 into this memory address of T2. I'm not storing it inside of T2, the variable. T2 holds a value of 4. So when I'm storing it, the value of T2 is 4, so I'm storing it in memory location 4, which is why I have the brackets at the side here of 4, and 5 is being stored in 4. Does that make sense?
Yeah.
Okay. Now I'm going to load from the memory address of 4. I'm loading that into T4. So again, any initial memory address that we see that doesn't have a value allocated, in this case, I think all of them, they don't have a value. So we know this is 4 in size. 4 is going to be loaded into T4. So T4 is going to be equal to, it's a memory address of 4. But then what I did is I added whatever was inside of 5, inside of T1, which was 5, into the memory address of 4. So when he called 4, 4 is currently holding 5 inside. So 5 goes into T4. Then for the next line, there's a 3, and we're adding the 3 to the T4 value. T4 currently holds 5, so therefore it's 5 plus 3, which is going to be 8. So therefore T4 is holding 8. In the store word, we're storing from the register into the memory location. T4 has 8 inside, so therefore the memory location of 5 is going to hold 8. In 4, I think currently we have 5, we wrote 5. So therefore 5 is being loaded into T2. So T2 currently holds 5. The next line it says T2, which is 5 currently, is going to be added to 1. So that's 6. And that 6 is being stored into T3. So T3 has 6. Then we're doing a load from the memory location of 2. Did we do 2 at any point in time? Oh, we had 2 at the start. No. Oh yeah, 2 at the start was initialized to 4. Because it's at any data memory location has a size of 4. So therefore 4 is going to be loaded into T1. So 4 goes into T1. Then we're doing T3 plus T1. T3 has a value of 6 currently. T1 has 4. So therefore T2 is going to hold 10. The memory location of 1, it wasn't initialized before, so therefore 1 has the value of 4 inside, so therefore 4 is going to be in T5. Then we're doing an add 2 plus the value is in T5, which is a 4 plus 2, so it's 6, therefore T5 was 6. Now we're doing a store. We're storing whatever's inside of T5 into the memory location of 3. T5 currently has 6, so 3 is going to be 6. Then we have 2. 2 here has 4. We saw it in the previous one. I think so. Memory location of 2. Yeah, 2 has 4. So therefore 4 is going to go into T6. T6 is equal to 4. Now for 15, T6 has 4. T1 has a value of 4. And T6 has a value of 4. So therefore T6 is going to be equal to 8. Then for 16, T6 has a value of 8. 8 is going to be loaded into the memory location of 3. Then 9, it wasn't initialized before, so therefore this is 9 is 4, and the 4 is going to be added to the T7. So T7 is equal to 4. Addition is happening of 3, so T7 is now going to be equal to 7. And we're doing a store word. The 7 is going to be stored into the memory location of T7. T7 is 7. So therefore, in the memory location 7, we're going to store 7. And the last line, the memory location of 3 has a value of 8 because it was updated in a store word. So the 8 is now loaded into T2. So T2 is equal to 8. Okay. And that's pretty much like how the code runs and the understanding of the code. Is there any question on any of the instructions? All right. There's no questions. We'll move on to the policy. Because I think in the second part it says do the direct mapping of the location, and then you do the total memory access time. Okay. If not provided, assume that each data we did that. Okay, so now we're doing the write through, write miss, do not allocate. So in the first line, the first instruction, it's labeled 1 to 20. So we're doing the first instruction in the first one. In the first one, the initial value is 2 and is being loaded into T2. Now for our cache, it says there's a cache of 2. So because the cache of size 2, we have a 0 and a 1 here. And currently, we know the value is 2. That's the value that the memory location that they gave us. The memory location is 2. So given that we now go into the cache, we see that 2 isn't there because our cache has nothing inside. We're going to have a write miss. So there's a write miss. On the write miss, it says do not allocate. So we don't allocate anything to the cache. Yeah. It goes to the memory. Okay. And then it was a load word. Okay, yeah. So it's a do not allocate. So it doesn't allocate anything to the cache, but it's a load word. So because it's a load word, we're loading something, the 2 gets loaded into after direct mapping because it says is direct mapping. So you're doing mod of whatever the memory reference value is. Therefore, with the mod of 2, it goes into the cache map of 0. So 2 is loaded into the cache. Now, in the second line, there's a add. The any instruction that I believe that isn't a load or a store, we do nothing. So we just skip those stages because if you look at your messy, we only have add and store instructions that goes through the messy. So if in this problem, you see that there's no you see when there's add, all I did is I skipped those. So anything there was an add or an R type, I skipped those steps, but I only did the load and the store because that's the only ones that you're concerned about for the messy. So in the second state, there was an addition happening. We're gonna keep track of the data for the addition, but it's of no use to us in the actual mapping that we're doing. So we're gonna go to step 3. Step 3 has T1. The value of T1 is gonna be loaded into the memory address of T2. The memory address of T2 is currently 4 because T2 represents 4 since in the steps, yeah, 2 was basically 4. 4 was loaded into T2. T2 holds 4. So the memory location of 4, so for this question, the memory location is 4. And there's a register of T1. We're taking whatever's in T1 and we're trying to load that into the memory location of 4. Now, when I go to this is my memory location of 4. I'm going to go to my cache. I do the direct mapping. It's going to do the mod of the 4, which is 0. So therefore, we see that there's a 2 in that space. Because there's a 2 in that space, on my right miss, I don't allocate. So therefore, the 2 remains in this step. Okay? On step 4, what I'm doing is I'm loading. So because I'm loading, it means I'm going to pull something from the main memory. In this case, I'm pulling the memory address of 4. So the memory address of 4, again, it's a miss because it's not inside my cache. So because I have to load it, I'm going to kick whatever's inside currently, which is a 2, and the 2 changes to a 4. Does everyone follow so far? The 4. In the third step, what I was doing is I was storing into the memory location. So because I was storing and it was a right miss, I do not allocate because that's what my step says. So when I miss, I do not allocate. So the 2 remained. I did the writing to the main memory, so it was updated. It was updated in the main memory. The main memory is somewhere over here. So in the main memory, that memory location of 4 is now equal to the value that they wanted me to store, which is 5. So 4 is equal to 5 in the main memory, but I do not allocate it. So therefore, the 2 still remains in my cache. I didn't put the 4 inside. But in the following instruction, the 4, it says I'm loading that memory address into the cache. So I'm going to kick the 2 out and I'm going to put the 4 in. If it was that it was a 5 or something that was loading into the cache, the 2 would have remained, but I'd put the 5 inside of the 1 because the mod of 5 would have been 1. Do we follow so far with the 3 and 4?
Yeah, so just to clarify, we didn't update on the third line because it was a store word.
We didn't update the cache, but we updated the main memory.
Okay, gotcha.
So that's why you don't see the 4 inside of the cache because it says do not allocate. But in the fourth step, it says that we're loading in the memory address of 4. That's why the 4 came into the cache on the step 4. But the update did happen. It was just in the main memory. But do not allocate because of our policy. We're not gonna load it into the main memory. Into the cache, sorry.
Okay, gotcha.
Good. So step 5, it's an add type. We're not gonna do anything. Step 6, it's a store word. We're storing into the memory address of 5, whatever's in T4. Now, when we go to the cache, we're gonna see that there isn't a 5 inside. So it's gonna give us a miss because we have nothing in this space. On the miss, it says do not allocate. So what I'll do, I won't put the 5 inside the cache, but I will update the 5 inside the main memory. So the 5 that the update in the main memory is keeping track of that inside here. But I'm not going to put the 5 inside of my cache. I'm going to skip to the next step now. Step 7 says we're doing a load word of 4. Well, 4 is already in my cache, so I get a hit because 4 was already added in the previous instruction 4. So I get a hit here. Step 8, there's an add, so we do nothing. Step 9, we're loading another memory address. So we're loading the 2. In this case, we went to the cache, we saw there isn't a 2. So what happened is there was a miss. So on the miss, because it was a load, we're going to kick the 4 out and we're going to put the 2 in. Step 10, it's an add type. We do nothing again. Step 11, there's a memory address of 1. So we're going to look in the cache. We're going to see a miss again because we don't have the 1 inside. But it does say that we're going to load that 1 inside because it's a load word. So therefore, when we do the mod of 1 by 2, it's going to give us 1. So therefore, 1 goes into the cache. So my cache is currently filled. I have the 2 and I have the 1 inside. I'll move on to the next instruction. That was still a miss because the 1 wasn't inside the cache. If the 1 was in the cache already and they wanted me to load something, it would have been a hit. Step 12, there's an add type. We do nothing in the add type. Step 13, we have the memory location of 3. And we're loading into that memory location. We're storing into the memory location of 3. We're going to look at the cache. We don't have 3 inside, so it's going to be a miss. On this, we do not allocate. So we're not going to put the 3 into the cache. We're going to update inside the main memory. So the main memory takes the value that's being stored into the 3, but we don't put the 3 inside of the cache. The only time you're putting something in the cache is when you load it into the cache. The next step says that we're loading 9. So we're going to look for, what was that, 17? Yeah, 17. So on 17, we're going to look into the cache. 9 isn't there, so it's a miss. But what we will do is we're going to replace whatever's inside there with the 9. So 1 was inside originally, so we're going to remove the 1 and we put the 9 inside. So the 9's here. It was still a miss because it wasn't in the cache. Well, 9 is now in the cache. In 18, we do nothing because it's an addition. In 19, we're doing another store again. We're doing a store word of whatever the value is for T7. T7 was 7 at the time, so we're doing 7 as the memory location. We look at the cache. The cache does not have a 7 inside, so therefore it's a miss. And on the miss, we're going to have to kick whatever value is inside out of the cache. Yeah, for 19. See, just to confirm. Yeah, so this should, yeah. So you kick it out, and then on 7, there was a right miss. Because it's 7 is the memory location, and you're loading 7 inside. So it was a miss. Yeah, and we do not allocate. Okay. Yeah. So we do not allocate. I'm getting confused with it. So we do not allocate. So the 9 remains inside, and we move on. But the updated 7 happens inside of the main memory. Then in step 20, we're doing 3. We look at the cache. 3 isn't in the cache, so we have a miss again. And because we're doing a load where we're going to load the 3 inside, so 3 goes in, it was still a miss. Okay, and then that completes the cache. Now at the bottom, if you keep track of the right misses, the do not allocates, and so forth, you're going to have a total idea of how many misses you had. So in this case, we had 1 miss, 2 miss, 3 miss, 4. There was 1 hit. 5, 6, 7. There's another hit. 8, 9, 10, 11. So we had 11 misses. The question says at the end, we're going to calculate the total time. So for a miss, it's going to be 20 seconds. So it's 20 seconds plus the penalty. Once the penalty is given for a miss, it's the miss time plus the penalty. And that's going to give you the calculation times the amount of misses for total misses. For the hits, once it's a hit, it would be the TC value, which is 2 seconds. And there were 2 hits, so it's going to be 2 times 2. In some questions, he puts the penalty still because there is kind of like a penalty for going to the cache, it takes 1 nanosecond to go to the cache, then to uplift the data. But I think in the exams, I'm not sure if he still has you incorporate the penalty inside, or if he just wants the value for the hit. So you guys could ask him before the exam. I don't think he either way he doesn't really like make it doesn't make a difference with the thing, but I know for some exams he did say that he wanted only the hit time. So just clarify that because in some of his sheets he does add the penalty and some he doesn't. But that's basically how the right miss do not allocate would work. Does that clear up the right miss do not allocate concept? Okay. We have like 5 minutes more. Is there anything else you want me to go over like briefly? Or I could give you like a couple pointers for? Because I think we spent most of it on like the messy and the do not allocate policies.
I just have a question. We went through the right through allocate and do not allocate where you update cache and memory and then you don't upgrade the cache and memory, but we didn't go through the write back policies.
Yeah, we didn't get to go through the right back.
So on write back write miss allocate, do we which one do we update on that one?
On right back, do not can you repeat it?
On write back write miss allocate?
Right back, right miss, allocate.
Yeah.
So the thing with the right back, right? I think I had asked someone earlier. Can you guys recall what the right back meant?
Update the cache, but don't update the memory when you need to.
Yeah, okay. Yeah. So that's what the wait. No, no, no. The the write back, you would update the cache, but then you update the memory later. That's what the write back does. The write through is the cache and the memory at the same time.
Oh,
The do not allocate means that you're updating the main memory, but not the cache. The allocate means that you're updating the main memory and you're also putting the value into the cache. Does that make sense?
yeah, I got it now.
Okay. But yeah, the write back, you're going to write to the cache first, and then you'll deal with the memory after. The memory is not like something that you do continuously. That's why a lot of programs they use the write through policy because it helps with duplicating or having a secondary copy of data in the main memory in case the program closes and the cache is wiped, you still have the data inside the main memory. But for speed, write back is better because it's only writing to the cache and you're using from the cache. Then after you would have done all the tasks that you need to do, then you'll update the memory after. Or whatever task it is, once you've done the task, then you'd update the main memory after. So there's a difference between the write through and the write back. One saves time, but one's good at retaining some of data if you were to lose power to the system. So again, when you're doing allocate, you're doing the main memory and the cache. When you're doing to not allocate, you're just updating the main memory, but you're never bringing anything into the cache. The write back, you're updating the cache throughout the policy, but you're not updating the main memory right away. For the write through, you're on the write miss. Okay, well, just the write through. For the write through, you're updating the cache and the main memory at the same time. Does that clear it up?
Yeah.
So we did the do not allocate and the allocate for the write through policy. We didn't get to do the write back ones, so you guys can practice that one. This video was recorded, so it will be uploaded. Hopefully by tomorrow it should be uploaded. Your exam's on Tuesday, right?
It's on Thursday.
Thursday? Okay, okay. And you guys don't see him before Thursday. It's just Thursday alone.
Yeah, we see him on Thursday.
Okay. So the video should be up by tomorrow, hopefully, if not by Monday latest. So you will be able to see the write through. Do not allocate and allocate. So you just have to practice the write back ones. I hope this was helpful enough for the exam. It gives you a start, and it simplified some of the things that you had ideas with that you can maneuver. And remember the cash system, the four-way and the two-way, that's probably going to be the most difficult ones. So practice those. The direct one's going to be pretty simple. And then the least, I think there's least recently used, and there's also first in, first out, if I'm not mistaken. So you need to go over that one as well, and the least recently used for the exam. But yeah, if you do the review sheets that he gave you and the problem sets from class, you should be fine for the exam because there's no trick questions in the exam. It's pretty straightforward. It comes from his lectures. Whatever you see there, that's exactly what you're going to see an idea of in the exam.
I have a question. Do you know, he also showed us the optimal version. Do you know?
Yeah. So optimal just means that you're looking forward. Like let's say for the data set, that's a good question because I think someone had optimal in their exam as well. I didn't get I think I had optimal for mine if I'm not mistaken. Where's the sheet? The optimal part was the simple part. It was just the four-way that I messed up. Um, Let me see. Yeah, so I had to do um it said a two-way set associative of okay, I see. Okay, so we'll go a bit over time, just like a couple minutes, because I think this is really important. So I had a cache of size 8. So this was the size of the cache. And it said here that he wanted to do a two-way set associative. So I thought that it meant that it's supposed to be only two sets, but because it was 8 as the cache size, it's not two sets. It meant two per each set, apparently. So this is what it means. 4, 5, 6, 7. So it's just, so this should be 1, 2. Will it be 0, 2, 3? Yeah, so that's what it meant by a two-way set associative for a size 8 cache. It means you only have two options per set. That's what it meant. So if it was a four-way for the cache, it would have been four ways, 0, 1, 2, 3, and then 4, 5, 6, 7 for the second set for a four-way set associative. So I made a mistake when I explained this. This
Wait,
is
so
what it meant
the amount of ways isn't the amount of sets, it's the amount of like cash blocks within the set.
within the set. Yeah,
Okay.
that's what it meant. Because for the exam, when I had a two-way set associative to do for an 8, I did two sets, but it wasn't supposed to be two sets. It was supposed to be two cash blocks per each set. That's what it meant. But the second part was the optimal part. So what optimal means is that you're looking at your data set, right? And let's say I saw like 7. I'm just gonna rewrite this. I saw 7 being used like 3 times in the future. I had 4 as my cache size, but I know after I loaded 7, 3, and 1. Oh well, let me just remove 2 of these. So let's say I had 7 and 7 here, right? So I know after I load 7, 3, and 1 into my cache, I'd have 7, 3, and 1, and then 2. All right, so that's how my cache block looks currently. Now, I need to remove 1 to put 5 inside. But if I look forward at the data that's currently ahead of me, I see 7 is being used for 3 numbers back to back. So I'm not going to remove the 7. After the 7, I see 2 is going to be used as well. So I loaded 2 recently, but 2 is going to be used here too. I see a 6 here, I see a 5, I see 3. So 3 is also going to be used there. I don't see 1 until all the way here. So to me, it would make more sense to remove the 1 since I can put the 5 inside, and then 5 is going to be used again, and 5 is going to be used again before 1. And by the time I'm done with that, 7 went through all of its stages, So, but there's still a 7 to be used. There's still a 5 after that, and there's a 1. So the ones that are currently in my block, which is the 3 and the 2. Okay, I think I might have confused you guys a little bit there. So let me just go over it again. So I load the 7, the 3, the 1, and the 2 in my block. 5 needs to be used inside of the set. So because 5 is going to be used, I need to remove one of the blocks. But I look forward to what I have, and I see 7 is going to be used 3 times. Then I see after that, 2 is also going to be used. So 2 I can keep in my cache. There's a 6, then there's a 5. I need to load the 5 in. So if I load the 5 in, I can keep the 5 in for 5 again. There's a 6, which means I need to remove something else along the line. Then there's 3, 2, 7. So I know to myself, with the immediate, when I look forward, 7 is going to be used, and I know 2 is going to be used. So therefore, I can either pick between 3 or 1 to remove from my block. When I look into the set again, I see the 3 is also going to be used. So I'll keep 3 inside. 1 isn't going to be used all the way until the end. So I'll kick the 1 out, and I'll put the 5 in place of the 1. So 5 would be somewhere here. Now, 6 is also going to be used. At this point, when I would have finished the 7, I don't have to use 7 until the next 4 numbers. Well, I need to use 5, which is currently my block. I need to use 3, which is currently my block. I need to use 2. So therefore, I will remove the 7 because these 3 are going to happen before the 7. But then, wait, I look forward to the data set and there's 7 again. Okay, so I see 7 here. I see 7 here. I see the 2 here, the 5, and the 5 here. There's a 6. Oh, so 6 will be in my block, but 6 is not going to be used. So I won't remove the 7. I'll remove the 6. Once the 6 is removed, I'm going to have 5, 3, and 2 in my set currently. Then I see 2 is going to be used again, 5 is going to be used again. There's a 1 that needs to be added, 7 is going to be used again, but 3 is not going to be used in the future. So I can kick the 3 out and I can put the 1 in when it's time for that. Then 5 is going to be used and 1 is going to be used. So the idea of optimal just means looking forward at the data set that's given to you, and you're trying to take whatever data that's given to you and try to assess how many times you think one variable is going to be used so it's most optimal to keep that one in my cache. But if there's one that's only going to be used one time and never again for the rest of it, I can kick that out and I can put something in that will be used multiple times. Does that make sense for the optimal? Yeah. So it's like predicting. That's what you're doing. You're predicting the shortest runtime. That's what you want because optimal is going to give you the shortest. So for that reason, you're trying to see how much you can maximize your cache by having something inside that's going to be used the most, and then for things that won't be used at all or just once, you can kick those out and put things in that will be used a lot more. So that's basically with optimal. The fully associative, the rest are pretty much easier. All right, but that's basically everything for the write back, write through, to allocate and allocate, and the mapping. So the write back you'd have to review and some of the cache mapping. And we did go through some of the like inline coding and steps, but we didn't get to go through like the execution cycle. You're gonna have to prepare yourself with the execution cycle. All right. I hope that was helpful, and best of luck on your exams.
Where will the recording be posted again? Sorry.
I think you should get an email when the recording's posted. But if you don't see it, it's gonna be on the Learning Commons channel, the
Oh.
YouTube channel for Learning Commons.
Okay, got it. Thank you.
No problem. Best of luck, guys. You're all welcome.